All right, for our last section of Module 14, we're going to keep talking about proving triangles are congruent, but this time we're going to focus specifically on right triangles. Now, the first thing I want you guys to know is that when you're proving that two right triangles are congruent, you can use any of the theorems we've learned before. So I wrote them there for you. SSS works for right triangles, SAS, ASA, AAS, they all still work for right triangles. And in fact, you kind of get one of the A's for free because we have this theorem that says all right angles are congruent. So if you have two different right triangles, that means each one has a right angle. You can automatically, like right after given, the very second step of your proof, you can say the two right angles are congruent. Reason, all right angles are congruent. You get one of the A's for free. So let's take a look at a proof together. We have a picture. It's two triangles kind of stuck together. It says given D is the midpoint of BC. Prove triangle ABD, which is the one on the left there, is congruent to triangle ACD, which is the one on the right. Now, before I start this proof, I want you guys to notice, if you look in the middle of the picture, you have that line with a right angle on it. It's where line segment AD meets line segment BC, and it shows a right angle. Now, even though it only shows one right angle, there's actually one right here also. So it might not show it in the picture, but basically anytime two lines meet and make a right angle, they're called perpendicular, and all the angles that they make there are right angles. So even though the original picture only showed one, there are two right angles in this picture. And now you can see we're trying to prove that right triangles are congruent. So I'm going to set up for a two-column proof. I'm going to make a statement and reason table. And like any proof, the first statement, we're just going to copy down the given information. So for statement 1, I'm going to say D is the midpoint of BC. Reason given. Now that's automatic. Now that's not something we can mark on the picture. As soon as you write something in your statement table, you mark it on the picture, but being a midpoint isn't something you can mark. It's going to help us get one of our S's, but it's nothing yet. Now before I do midpoint, let's do that automatic step I talked about on the last slide. There are two right angles in this picture. Let's say they're congruent, but make sure you don't just say angle D. Because remember our rule for angles, if there's more than one possibility, you have to use three letters. If I said angle D, you wouldn't know which of the right angles I'm talking about. So what I'm going to do is I'm going to say angle, and I'll call the first one BDA. See, I'm going from B to D to A. That's angle BDA. That's the right angle right there. And then I'm going to say that's congruent to angle, and then I'll do the same thing on the right side. That would be CDA, angle CDA. Now remember, the reason for that, the reason we know they're congruent is they're both right angles, and all right angles are congruent. So that's what I'm going to say. All right angles, I'm going to use the angle symbol for angles, are, and then I'll use the congruent symbol for congruent. So it's okay to use shorthand notation like that. You don't have to write out a full sentence. I said all right angles are congruent. All right, so basically I have one of my A's. Now I look at the picture and I go, okay, well, what else do we have? Let's go back to that given. D is the midpoint of BC. We know that midpoints cut things in half and create two congruent pieces. So let's say that next. BC is the bottom. So if I cut it in half, that means line segment BD, the left-hand side, is congruent to line segment DC, the right-hand side. Now for the reason, I'm going to say the definition of midpoint. And remember, I've told you guys before, if I see the word midpoint anywhere in your reason, I'm going to give you credit for that. If you said midpoint theorem, or if you said because D is the midpoint, anything at all about midpoint, I'm going to give you credit for. I'm not super picky about definition versus theorem versus postulate, as long as you have the concept right. So let's mark that on our picture. That's the first thing we need to mark. BD is congruent to DC. So I have one S and I have one A. I need one more side. I need to find another angle or another side to see if I have the right combination to use one of my letter theorems. Now, I noticed the thing we talked about last week. Whenever you have the two triangles stuck together so that they're sharing a side, you can say that side is congruent to itself by the reflexive property. I'm basically going to say this side down the middle, AD, is one piece of both triangles. So whenever I notice that, I say for my statement, AD is congruent to AD. You say, of course it's congruent to itself. It's the same thing. It has to be the same. Now the reason for that one is always the reflexive property. Reflexive property is the one where you say anything is equal to itself. Now, if you look at what we have here, we have our triangles are congruent by SAS, because what we have is, let's kind of circle them up here. We have side, angle, side in one triangle, and then we have the same side, angle, side in the other triangle. That's SAS. So I'm ready to say, remember what we're trying to prove. If you look up at the statement where it says prove, I'm ready to say that triangle ABD is congruent to triangle ACD, and my reason is going to be SAS. Side, angle, side in order. We had the side on the bottom, then the right angle, then the side that's the same in the middle, SAS. So we did our proof, and remember, the proof is always kind of broken up into three steps. Step one, just state the given. That's easy, automatic. Step two is the work, where you have to find enough S's and A's to use one of our theorems. And then step three is the conclusion, where you say this, whatever you're trying to prove. And if you're trying to prove triangles are congruent, your reasons are the letter theorems, things like SAS, or we could have done in a different proof, maybe SSS, or ASA, or something like that. All right, so what we've talked about so far is what's the same about right triangles. We said it doesn't matter if they're right triangles, you can still use the same four theorems. What I want to talk about next is what's different. So we're going to learn a theorem today. It's called the hypotenuse leg congruence theorem, or HL for hypotenuse leg. And it says if the hypotenuse and one leg of a right triangle are congruent to the same thing in another triangle, then the triangles are congruent. So let me go over those words, hypotenuse and leg, with you, just to make sure you know what they mean. So let me draw a right triangle here. Here's a triangle. I'm going to put the little box in this corner so you know it's a right triangle. Now every triangle has three sides, and when you're naming the sides of a right triangle, the hypotenuse is a very specific side. It's the one opposite from the right angle. So if you find the right angle in your triangle, which is the little red box there, and you go to the opposite side of the triangle, that's the hypotenuse. It's also always the longest side of the triangle, but you don't always know that. It's definitely the side opposite the right angle. Now the other two sides we don't have separate names for it. They're both just called legs. This is a leg, and this is a leg. So basically every right triangle has one hypotenuse, that's the longest side, it's the one opposite the right angle, and then we just call the other two sides legs. So if I had two right triangles, and I could show that the hypotenuse was congruent in both of those triangles, and I could show one of the legs, it doesn't matter which one, then those two things are enough by HL to say the triangles are congruent. And here's a picture of the HL theorem. So in this picture right here, we have triangle ABC, and then we have triangle XYZ. And what you notice is, number one, they're both right triangles. Angle C and angle Y have the little box in them that shows you they're right triangles. And then number two, the hypotenuse is the same. Remember, hypotenuse is opposite the right angle. And it's the same. One mark here, one mark here. So that's your H. Then we have another side. Doesn't matter which one. This side here, congruent to this side here, that's your HL. So you could say that the triangles are congruent by HL. Now what I want you guys to notice real quick is if we didn't know HL, what you're actually looking at here, if you think of it in terms of like last week's lessons, This is the SSA triangle that doesn't work. You have side, side, angle. Side, side, angle. That's the one that doesn't work. So what we're really saying here is that no, SSA doesn't work for proving triangles are congruent, but it does work if it's a right angle. So instead of trying to think of it that way, that can be very confusing. If we try to remember it that way, like SSA doesn't work unless the angle is a right angle, then it does work, that's way too confusing. So we gave it a new name. We call it HL instead, but that's basically what we're saying. We're really saying when we do the hypotenuse leg theorem, or HL, we're really saying that SSA does work as long as that's a right angle. So let's do one last proof for today. This will be it. Here we have a lot of triangles in this picture, actually. I drew what looks like a rectangle, although we're not going to assume it's a rectangle. What looks like a rectangle, and I drew the two diagonals. I drew that X going through it, and it creates a lot of different triangles here. There's 4 that you can see, but also you'll see when we get to our proof that we're actually looking at the big triangles, like 2 combined in 1. But let's go ahead and start our proof. Here's my statement and reason table, and just start with the automatic. Start with step 1, restate the given. So I'm going to say angle DAB and angle DCB are right angles. And also I'm going to say line segment AB is congruent to line segment CD. Reason given. All right, let's mark some of that stuff on the picture. Angle DAB is that bottom left corner there. So I'm going to put the right angle marker there. And angle DCB is this top right corner here. So I'll put the right angle marker there. And then AB, which is the left side over here, is congruent to CD here. All right, so we got our given. We got our information marked on the picture. Let's look at what we're trying to prove. Because remember, sometimes a proof is easy. If there's only 2 triangles in the picture, then you go, yeah, I'm trying to prove they're congruent. Easy. But this one, we got to figure out what we're being asked to do. So let me highlight them in different colors here. Triangle ABD, A to B to D, is this big one here. It's not one of the little triangles. It's 2 of them combined. And triangle CDB, C to D to B, is this big purple one over here. So we're not looking at 2 of the 4 small triangles. We're looking at half of the rectangle, basically. Each half we want to prove is congruent. So now that I kind of highlighted it in purple and green, it's a little easier to see what we have here. So what we have is, we have a right angle. We have one side marked congruent, and it's not the hypotenuse. The hypotenuse is actually the diagonal line going down the middle. It's line segment BD, because that's the one that's opposite from the right angles. And in fact, we can use reflexive property on line segment BD. So let's do that first. For our next step, let's say line segment BD is congruent to line segment BD by the reflexive property. Everything is equal to itself. And I'm going to mark that on the picture. So I put 2 lines on the one line segment because I'm saying it's congruent to itself. And actually we have HL now. I don't need to do anything else. I don't even need to say the right angles are congruent to each other. Like in my last proof when we did SAS, I had to do an extra step where I said angle BAD is congruent to angle DCB, reason all right angles are congruent. I don't need to know that for HL. It would be an extra step. You could say it, it wouldn't be wrong, but it's unnecessary. So what I have in my 2 triangles is I have, number 1, the hypotenuse of each one congruent to each other. That's my H. And then I have any other side. I have this side congruent to this side. That's my leg. So I am ready to say, I'm ready to do the proof. So I go back up to what I was trying to prove. I'm ready to say that triangle ABD is congruent to triangle CDB. And the reason is HL. The hypotenuse and one of the legs is congruent in the two right triangles. They're congruent by HL. So that was actually, it looked like it might be a hard problem. It was actually kind of a simple one because it only took 3 steps. We stated the given, we did reflexive property for the hypotenuse, and we had HL. We were done. So the thing I want you guys to notice, a lot of times what students do is they see the right triangle and they automatically just think, okay, this is an HL problem. But remember the first question we did today. We did right triangles and HL would not have worked for that one. The one we did first worked by SAS, and really that was kind of the only way to do it. So don't forget, the very first thing I started notes with today, just because it's a right triangle doesn't mean the answer is automatically HL. Any of the other 4 theorems also work. SAS, ASA, AAS, you wouldn't use SSS because 2 sides is already HL. So, I mean, it would work, but it would be extra work. You don't need to show the third one. But really, any of the theorems work. So we have one new theorem, HL, for you to consider for right triangles, but remember it only works for right triangles.